And and today we will finish the main part of the crash course on conformal field theory. I did not decide whether next week I will move immediately to another topic or whether I will cover some slightly more advanced topics in conformal field theory now that we are specialists in CFT. But, okay, I will still think about it over the weekend. So, one very important idea that we saw yesterday was the idea of the state operator correspondence, an idea that we can radially quantize a conformal field theory by thinking that you can always, if you have a bunch of operators, you can always center your coordinates such that one of them is at the origin. And you can use radial coordinates where you draw circles around the origin. So you can have one operator at some radius e to the tau 1, some other at e to the tau 2, and so on. And under a conformal map, under a Weyl transformation, this space is equivalent to a cylinder where tau equal to minus infinity means you put the operator at the origin. Putting an operator at the origin means choosing boundary conditions at the origin for your path integral. So it means choosing your wave function in the cylinder at minus infinity, which is equivalent to considering your states in the cylinder. Remember, this is the cylinder where you have some time and you can do normal canonical quantization, and you have operators and you have states and you have some Hilbert space. So this O that belongs to some Hilbert space that I'm going to remind you what was this Hilbert space that we concluded. And then you can consider that you start with this state, which is dual to this operator at the origin. There is this very important operator-state correspondence. And then at some time tau 1, you act with some operator O at some point tau 1 and some n1, and so on. Then with some operator O corresponding to time tau 2. And at some point, you have some other state in your Hilbert state, some state psi. Okay? So this is the picture that you can consider operators or states and statements about, say, action of generators on operators. This we wrote all of this before. Here I added something that last time I did not write. I mean, last time the only thing I said was scalars don't rotate. Right? I just said scalar doesn't transform under rotation. What if we consider an operator that has an index A that is an index of some irreducible representation of the rotation group? If it's a vector or something. Well, then the index rotates accordingly. This guy would be a finite spin matrix that will tell you how the indices transform properly under SOD. Okay, but for a scalar, this would be 0. There is no transformation. It's trivial. So that translates into the statement that there is an Hamiltonian whose eigenvalues are the energy. There is a generator that kills the state. And most importantly is the observation that in conformal field theory, our Hilbert space organizes as a bunch of primary operators. Primary are highest weights with respect to this special conformal generator K. They are killed by special conformal transformations. Okay? So they define a set of operators of your theory, a very special set that are killed by this K. And starting from any of those operators, you can use P as raising operators to create operators that have dimension delta plus 1, delta plus 2, delta plus 3, and so on, which are what are called the descendants. And in terms of operators, they are just derivatives of operators. If you have an operator, you take a derivative. Because derivative has dimension 1, you just increase your dimension by 1. And correlation functions of primers and of descendants are, of course, simply related because the one is just derivatives of the other, so you just take derivatives of the correlation function. Then one immediate outcome of thinking in this term of this duality was the notion that if we now impose that in our quantum mechanical right-hand side, if we impose that norms of states are bigger than 0, a state is obtained by, say, some P times O, the conjugate state is K times O, we use the algebra of P and K that we found out, and we easily end up with bounds on the dimensions of operators. Okay? So we have now lower bounds, which are called unitarity bounds. It would be awesome if we would also have upper bounds, and that's what I didn't decide if I'm going to cover or not on Monday, but this would be the most standard thing. Okay, very good. Any question? Okay. Today I'll try to be very slow, because yesterday I had the impression that I might have been a bit fast. So I'll try to make an average, a reasonable average. So yesterday I presented 7 pages. Today my goal is 3 pages. I could even tell some jokes. Okay. Very good. So we have some state psi Now, the notion, a very important notion, will come about in a rather straightforward way. And that's the notion of the operator product expansion. Or OP. The operator product expansion, as we said before, is the following statement. Let me first write a formula that for some of you it might be so natural that it almost doesn't merit justification, but let me write it. It has the following. If you have some operator OI at some position x, and some operator OJ at some position, say 0, if you see them from very far away, you don't notice that it's two operators, one at x, one at 0, that there are two operators, or just a slightly more complicated operator. You could imagine that to leading order, these two operators, they look like a composite operator where you just replace x by 0, say. And then, to subleading order, you have O times derivative of this guy, and then O times second derivative of this guy. And so on. You can roughly, if you are very far away, roughly Taylor expand this guy around 0. So maybe it is not totally, maybe it is almost straightforward to imagine that you could always write this as a sum over all operators in your theory of some coefficients, C, I, J, K, that could depend on this position x, times the operator OK at, say, some position 0. Okay, so this is the statement. The statement that if we zoom very far away, we do not distinguish these two operators from a single operator or from a sum of single operators inserted at the origin. Very much like a dipole expansion when you have some complicated charge distribution and look from very far away. The first approximation is just a sphere with some charge. Second approximation is some dipole, and so on. Now, from this point of view, this is very natural because what we are saying is the following. And it even generalizes for more operators. Here, for example, suppose we have three operators. One at 0, one at tau 1, one at tau 2, and we are here at some state. Okay? So we have some operators inside this sphere, and we consider some sphere. And then what we notice is that whatever we have, the functional that we have from doing our path integral in this sphere is given by some state here, psi. But this is some state in some Hilbert space. So if it's a state in a Hilbert space, I can, of course, decompose this guy as a sum of some coefficient Ci, or let me write it Ck, times some operator, some base of some states in my Hilbert space, OK. Just because it's a state in my Hilbert space. And because it's a state in my Hilbert space, of course, this statement in the dual language, in the language on the left, is nothing but a statement that I wrote there. So that's it. This is, if you want, this is a proof. It looks so trivial, it almost doesn't look like, but it is. Now we can understand a few interesting things about this statement. When is this statement valid? When am I allowed to do this? Well, I'm allowed to do this always. Unless this tau 2, for example, I have some expansion, and then I decide to change tau 2, and tau 2 goes through the yellow line. Then something goes wrong. I no longer have the right of saying that this psi is the state generated by these three guys. Okay? Similarly, suppose there is an operator here, some O at some tau 3 and 3. Some operator that is further up in this cylinder. Suppose this is tau 3, and there is some operator here. So this tells me that this expansion is valid as long as tau 3 is bigger than tau 2. If tau 3 starts hitting this state, then this expansion is not valid, and I have to recompute the state because O3 acts first, and then I have to re-expand it. Yes? So it tells you very well what is the radius of convergence of your OP. If you have some operators and surround them by a sphere, the circle where it touches the next operator So this distance here is the radius of convergence of the OPE of the three operators. And similarly, for example, if I consider just the two inner operators, this would be the radius of convergence of the OPE of the two operators. Okay, very good. And now we can easily see that this could be very, very powerful, because imagine we have, say, a correlation function of 4 operators. Okay? And decide to expand them. And decide to expand these two guys around some point, doesn't matter what, it can be some point, it can be centered around here. It doesn't need to be centered around one of the operators, it can be whatever you want. And let me expand these two guys around some center here. You see that there is a big radius of convergence until it hits the next operator here. So this guy, it has a huge radius of convergence. Similarly, these guys, they have some huge radius of convergence. Let me even write this guy here so that. Okay. So we can really replace two operators, O1, O2. We can expand them, and we draw typically this diagram. We can expand them around any point that we want. And similarly, O3 and O4, we can expand them around any point. And at the end of the day, all we have to do is compute a two-point function. And there is a perfectly huge region, a finite radius of overlap, okay, where this procedure converges. And once we have the result in some finite region of space, we can analytically continue and get the result everywhere. Yes?
So in the expansion there, psi equals the sum and the...
Yes.
So the states, the basis vectors, I'm not sure if I understand. Which states are these? For example, in terms of
the states are exactly these states. They are a bunch of primaries and the descendants. Okay?
And in terms of the picture, is it easy to see? So you're saying they're somehow related to being beneath the yellow curve in the cylinder? Or
yes. So whatever set of operators I insert here, I generate here some state, because I have some state in my Hilbert space. If you want, okay, one way to think, you have some wave function. Now, if you want, you can undo the path integral backwards. And whatever you get by undoing the path integral, it will be something here. And that something here defines a set of states.
You could not have immediately taken the whole cylinder or something.
Sorry?
You could not have immediately taken the whole cylinder.
Put the state here, up here? I could. Here, I will have a new state psi prime if I act it with one more operator. Right? Is it clear?
I'll think about it.
Anyway, so there is, again, please ask, yes?
What do you mean by radius of convergence of the operator?
Radius of convergence, I mean that if I plug this expansion inside an operator, inside a correlation function, I might wonder whether this expansion is just asymptotic, and whether it makes sense to, inside a correlation function, inside a 4-point function, am I allowed to take O1, O2 and replace them by this, take O3, O4 and replace them by the same thing, and then just use 2-point functions between these two effective operators. If I do this, and if I take more and more operators, does it converge towards the real result, or is it an asymptotic series and I have no chance of getting the good result?
In what sense it converges? I mean, what's it wrong?
It converges in the sense that if I consider some operators, there is a region, a perfectly valid region where the OPE is valid, and unless I take these operators and make them go through this circle, you see? So if I start some operators, O1, O2, O3, O4, and O2 is closer to O1 than O3 is.
Can you write a mathematical expression?
Okay, we will write in a minute. I just want first to motivate, but in a minute I will write an expression for what does it mean to perform this picture here. Okay? Right. But okay, but let me, before moving on, what I'm saying is that this operator here is closer to this point than O3 is, right? Is it clear? If I start moving this point further and further, analytically continuing the position x2, at some point x2 goes through this line, and then I'm reaching the radius of convergence. Then the expansion I started with, I no longer have the right to expand. I no longer have the right to say that these operators can be replaced by an effective operator if this operator is so far away that there is someone that is even closer to the one than this guy is.
At the same time, you want to express in that point, you make sure that between the 2 points there's no
Exactly.
operator.
Exactly. I want to make sure that I can draw a sphere surrounding these operators and nothing else except these two guys are inside the sphere. Right? This is logical, right? So if I want to look from very far away and replace that sphere by something, not replace the two operators by something, better be that nothing else is inside that sphere. Otherwise, I don't have the right to ignore that something else. I also have to take it into account. But actually, we will see that we can do even better because we will be able to extend this radius of convergence from this notion to the full space by resumming the contribution of by resumming some particular set of contributions, which are the descendants. But that will come in a minute. Okay, very good. So this is the statement of the OPE. And it promises to be very powerful because what we are anticipating is that by successfully using the OPE inside correlation function, you see that if you can control this coefficient, Ci, j, k, you can, two at a time, start reducing the number of operators until you are left with just 2-point functions. So that's the main idea, is try to understand what do we know, how can we fix these C's. Okay. So the question is, what do we know about these guys? And these are called the OPE structure constants. Okay. And the next natural question is how to use the OPE to compute correlation functions. Okay. Okay, very good. So, the first thing that I want to point out is that so we have this sum over I, some coefficient Ci of x, OI at 0, where this sum over I is a sum over all operators. It's a sum over all possible states of your Hilbert space. But our Hilbert space separates very nicely into primaries, which are really the key guys, and descendants that are just derivatives of the primaries, that in a way we believe should be obtained from the primaries just by using the conformal algebra. So it is very promising, and we should do it, separate this into a sum over primaries k, and then we will have some ck of x times ok at 0, plus then we have a descendant. A descendant is a derivative ck mu of x d mu of ok at 0, plus two derivatives c mu1, mu2 k of x d mu1 d mu2 ok at 0 plus etc. Okay. So this stuff here is the contribution from the descendants. Okay. So one thing that you can immediately see is that these guys, O, they transform in a given way under dilatations. We saw yesterday in the very beginning, right? This guy transforms in a certain way under dilatations. So immediately you can read how this one transforms under dilatations by imposing that the left and right hand side transform in the same way, right? One thing you can also do is see that if this guy has some weight, this guy has one more derivative, so this has a weight which differs by 1, and so on. And this is the statement that these C's, they are less and less important, which is the statement that if you have a bunch of charges, you can just replace by the charge, plus the mono, plus the dipole, the quadrupole, and so on. Okay? So again, the statement is that under x going to lambda x, OI goes to lambda to the minus delta I OI. So this C mu1 mu n k goes to, if you impose that the left and right hand side transform in the same way, there is delta k minus delta 1 minus delta 2, you see, because left hand side transforms with delta 1, delta 2. Right hand side, there's delta k, but then there's the number of derivatives, so plus n times ck. So this means that the operators ck are more and more suppressed as x going to 0. Okay, so this means that as x is going to 0, C mu1 mu n are more and more suppressed. We will see this explicitly because we will compute these guys. I'm just saying that we could just anticipate just by counting powers of derivatives. Okay, so let's see, what do we know about this Cis? What do we know about the Cis? So, the way we will proceed is we will follow this idea of inside the correlation function replacing 2 points by their expansion, but we will not start by a 4-point function, but rather by a 3-point function. So we will have O1 at 0, O2 at x, and then let's put OK at y. And what is this? Well, by conformal symmetry, we saw that this is just C12k divided by, so let's write it, the distance between the first two guys to the power delta 1 plus delta 2 minus the third one, which was delta k. Let's do the next one. 0 minus y is just y. Delta 1 plus delta k minus delta 2. And similarly, for the last guy, x minus y to the power delta 2 plus delta k minus delta 1. All right. Okay. So now the idea is we will plug the expansion O1, O2, the OP, inside this 3-point function. But before I do so, let's continue manipulating a bit this 3-point function. And let's write it in the following way. Let's see, let me think. How do I want to do it? I want to do the following. Let me write it in the following way. C1, 2k. And let me factor out the pure power of x. X to the power, okay, delta 1 plus delta 2 minus delta k. Let me factor out y. to the power of the sum of those two guys. The sum of those two, delta 1 and delta 2, cancel, so it is just what? 2 delta k, if there's no mistake. Okay, it seems okay. And then, let me write what remains as 1 minus, I'm computing the square of that. Let me write and you can tell me if it looks okay to you. 1 minus okay? So all I did was, I wrote this as the square of this distance, and then I put this exponent over 2. I computed the square. And you see that I factored out y squared, and that's why this power of y has some funny power. And there is some finite probability that I did some mistake, but hopefully not. Now, for example, I clearly did. This could not be a plus. Okay. Does it sound good? It's no fancy manipulations, remember? So a distance x minus y squared, I just computed what it is, x squared, y squared, x dot y, I factored out y. Because I'm going to remember to think that x is close to 0 and y is very far away, so I want to put it in a way that it's ready for being expanded at large y. Okay? So the goal of this simple manipulation was just to write it in a way that I could now readily expand at large y. Okay? And we can do it. So as we said, we can expand at large y. And to simplify our life, let's do it when delta 1 is equal to delta 2. I leave it as an exercise for you to do it for the general case if you want. And then we get C1 2k divided by absolute value of x to the power 2 delta minus delta k. Then there is absolute value of y to the power 2 delta k. And then let's expand at large y. So these guys are the same, so they don't matter. And then we get just delta k. And when y is leading, the first one is the important, the second is the important one. The 2 cancels with this over 2. So we get 1 plus delta k over 2 y mu x mu, I'm just writing the scalar product explicitly, over y squared plus dot dot dot. Okay. Is it clear? Is it okay? Do you agree with the factors and so on? The 1/2, the signs and so on. So please, as I said, today we can do it a bit slower, so please see if you are happy. Does it look okay? Okay. So this is, if you want, what we expect from the 3-point function. But now, on the other hand, we can plug the operator product expansion. So that same expression should be equal to, we plug the operator product expansion there, and we get a sum over, let me use some other index, say k prime, which are the primaries. Okay. And then I have this big bracket that we wrote there. Correlation function between that big bracket over there times the operator OK at y. Okay. So this is this bracket here. But this is just equal. I can simply remove this sum and set here k prime equal k, because you remember that states, different states, are orthogonal. right? States with different deltas were orthogonal. Different primaries, they are orthogonal to each other, right? Of course, so here, this first guy there, OK, only talks to OK prime of 0, only talks to OK if they are exactly the same. Of course, the descendants are just obtained by derivatives of the two-point function. They are not 0 as well. So immediately we get rid of this sum k. And what we get is just the stuff about the descendants. What we get is ck of x times correlation function of OK of 0, OK of y, plus ck mu of x, correlation function, or d mu 1 means derivative with respect to the first slot, correlation function between OK at 0. Okay, let me do it like this. OK at z, OK at y, and then put z equals 0, plus dot, dot, dot. Okay? Just a derivative, but the derivative of operator, I can just compute the correlation function, take the derivative with respect to z. Okay? So this derivative here is with respect to z. Plus dot, dot, dot. Okay? And this is equal to ck of x, 1 over, and now if we compute that, is 1 over y to the power 2 delta k, plus the derivative, which gives c mu k of x. Now you take the derivative of a two-point function. What gives the derivative? It gives 2 delta k y mu divided by absolute value of y to the power 2 delta k plus 2 plus dot, dot, dot. Okay? Can you read what is there? I can raise it. Okay? So now all we have to do is compare both expansions. And we see that by comparing both expansions, by imposing that they are the same, we read off immediately what are these ck's. So what we conclude is that ck of x is just equal to, well, it's given by the three-point function c1 2k divided by absolute value of x to the power delta 1 plus delta 2 minus delta k. We were choosing deltas to be the same, so 2 delta minus delta k. And then we got that ck mu of x was equal to the same thing, but then we take the second term. Where is it? Yeah, that one. Those two terms should match. So you conclude that ck should be what? Should be x mu, you see, because that should be an x mu to match that term. The delta is already there. Okay. Sorry, 1 second.
Maybe a factor of 1 over 2 was wrong.
Yeah, I suspect so. Where was it?
At the top right, the delta k over 2, I think it was just delta k.
Ah, good, thank you. Yes. So at the very top, I was indeed looking for a factor of 2. Okay, so there, when I expanded, there is a 2 multiplying x dot y. There should be no over 2 here. Okay. So then, this guy gives just times x mu over 2. Is it okay now? Yeah. And in general, what is easy to see is that if you have general mu1, mu(n) of x, this will be equal to C12k divided by absolute value of 2 delta minus 2 delta k. And then some general tensor B, mu1 up to mu(n), that is a function of x. But this tensor here is totally fixed by conformal symmetry. Okay? So again, all we need to do is expand, collect powers of y, and impose that this expansion matches order by order. And as you see, we just worked out the first one, but in principle, we could continue expanding further the 3-point function, expanding further the OPE, collecting term by term, and in this way, getting information about these 3-point functions. That, as you see, are more and more suppressed for small x. They have this overall factor which is in common, but then this guy has 0 powers of x, this has 1 power of x, this will have 2 powers of x, 3 powers of x, and so on. So they are less and less important as x is small. Very good. So this is an extremely important point. So please take a minute to see whether it is clear or not. So what we want to summarize is the following, is that this ck of x, okay, are directly related to a quantity that we found already before. They are related to the 3-point functions. So this C12k that appeared before, the object that we said was very important, that governs the behavior of 3-point function, also governs the OPE behavior of 2 operators. Okay? So the OPE structure constants are the same as the 3-point function of operators. If you know 3-point function, you know OPE coefficients and vice versa. Okay? So this is very important. So it tells us that this is in the root of what I said in the very beginning when I told you that these deltas and these c's, the structure constants and the dimensions, will allow us to fix completely any higher point function. Now you see why, because if you know the 3-point function and 2-point function, you know the structure constants and the dimensions. But then, if you know the structure constants, you know how to take 2 operators together. When you take them together, you just get the structure constant plus a bunch of contributions from the descendants, but those are totally fixed by conformal symmetry. So then you see that, I mean, now at this point, we already understand that conceptually the problem is solved. Now it's a question of working out the details and seeing how to resum this kind of expansion. Okay? Okay, very good. Any question here? Yes.
Can I clarify the when you wrote ck mu1 to mu(n) goes to lambda delta k minus is delta 1 minus delta 1 minus delta 2 all the way to minus delta n?
Sorry? Can you repeat?
That in the second board?
Yes.
Did you have the typo there? When the ck to lambda to the power of ck, that there's an n there. So
yeah, n is related to the number of derivatives. So the more derivatives you add, the more suppressed you are. You see, when you rescale x, rescaling x means that you basically count how many powers of x there are, right? So saying that something scales in a given way as you rescale x is basically telling you what's the homogeneous degree in x that it has. So how suppressed is it when x goes to 0? It's what it is telling you. And you see that this guy goes with 2 delta minus, here there is a 2 which is wrong, 2 delta minus delta k. And this next one goes to delta minus delta k plus 1. And then this y plus 2 and so on. This guy is more suppressed. You see, this one, this here, this one is this n equals 1 in that expression. The fact that there's 1 more power of x. Okay? So you see, when n x goes to lambda x, this guy transforms in this way, right? When n is equal to 0. If you do here, x to lambda x here. You agree? This guy transforms in this way when x goes to lambda x. Okay. Is it clear? Do x to lambda x here. You get lambda to the power delta k minus 2 delta, which is this. Right? If you do it here, x to lambda x, you get delta k minus 2 delta, but then plus 1 from this guy that is here. So you get the plus n there. And so on. Okay, very good. So now, is it clear? So now let's then see this promised picture that I was showing, how to then use this. So okay, 2-point functions and 3-point functions we knew already in any case. How can we do it now for the 4-point function? So how can we see that this machinery is very powerful for the 4-point function? But before, let me have a disclaimer. Let me tell you that we are ignoring spin. Okay? So up to now, we are ignoring spin. So let's write this here because by this I mean that in the OP of two operators, I'm assuming I only produce scalars, and that's of course not true. I can also produce states which have some spin L. Okay? So at the end, I will tell you what changes when we include spin. So for now, just in case you would complain, I could in principle produce a state with spin L, of course, in the OP. Okay? And I will. Okay, but let's continue our simple discussion, assuming that in the OP of two scalar operators, we would only get scalars, and let's continue. And now let's consider a 4-point function. So suppose we have a 4-point function, O1 at x1, O2 at x2, O3 at x3, O4 at x4. And let's do what we said. Let's apply the OP. Let's replace these two guys by some operator, OK at the origin. So then what do we get? We get the sum over the primaries k. Then we get the sum over n from 0 to infinity, which tells you how many derivatives you get. Then you get this C12k times, okay, I apologize, but okay. Let me redefine the b here, sorry, in the last line. Let me define the b as being all this, okay? I can always absorb this factor here also. It's more convenient, okay? Please absorb this factor inside b. So there is some C12k, and then there is some b, which I know, mu1 up to mu n, which is a function now x1, x2, so of x1 minus x2. Again, very important to emphasize. This guy is fixed by conformal symmetry. Okay? So this is fixed. This I know what it is. It is some function that I know what these guys are. This is not fixed. This is the interesting part. This is the dynamical part. And then what we have? And then we have derivatives of the correlation function of the operator And what does this correlation function give? Well, it gives again some structure constant times some space dependence. So I can write this as some sum over the primaries k, C1, 2, k, C, k, 3, 4, times, so I took it out of the sum over the primaries, and then I have sum from n equals 0 up to infinity, some known b1, b mu1, b mu n, some known tensor that I can fix. The first two guys we fixed them, of x1 minus x2. Derivative dx1 mu1, derivative dx1 mu n. What is the 3-point function when I took out the structure constant? It is just a space dependence, 1 over x1 minus x3 to the power delta k plus delta 3 minus delta 4, x1 minus x4 delta k plus delta 4 minus delta 3, and x3 minus x4 delta 3 plus delta 4 minus delta k, totally fixed again by conformal symmetry, the space dependence. So all this block, whatever it is totally fixed. Okay? It's extremely important. All this block, okay, all this block is fixed. It's known. I know what it is. It's a function. Okay? It's as good as cosine or sine or spherical harmonic. Actually, it's very similar in spirit to spherical harmonics. The physical meaning is roughly the same. This function is a purely kinematical function, so it's purely kinematical. Doesn't contain dynamics. It just follows from the way the conformal group, So this function here, we can denote this function as some f k that depends on this 1, 2, 3, 4 labels. That also depends on the deltas of the 3 external guys. And it depends on x1 up to x4. And this function is what is called the conformal block, or conformal partial wave. And it's some function that in principle you compute all these b's, you just resum this, and you get some function of delta 1, delta 2, delta 3, delta 4, and delta k. But which is a totally known function. Actually, I will write it explicitly in 5 minutes. It's a bunch of hypergeometric functions. It is known. So the cartoon is that we can write any 4-point function as a sum over k of some exchange of some operator OK. So this cartoon, what does it mean? This structure, you first take operator 1 and 2 and fuse them. Then they propagate. And then you overlap with operator 3 and 4. Right? And you consider a correlation function as a scalar product between the state that between whatever you produce here and whatever you produce here. Okay? So this cartoon means this formula. When I write something like this, it means 3-point function times 3-point function times what is called a conformal block. Okay? This conformal block is very similar to spherical harmonics. Spherical harmonics are the functions that you use to describe propagation of particles with definite angular momenta, for example. And here these are propagation of particles which generalize, which have definite dimension, definite conformal dimension. Very good. Of course, we know what the total dependence of this guy should be. So we know that this function, let's now focus on operators of the same dimension. Yeah, let's focus on operators of the same dimension. Then we know that O at x1, O at x2, O at x3, O at x4 should be equal to 1 over x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta, times some function we said that only depends on 2 cross ratios u and v. So it is not very smart to work with 4 variables, 4 vectors. You are working with 4 vectors with like 16 variables, right? X mu, x1 mu, x2 mu, x3 mu, when in fact it only depends on 2 variables. So of course this conformal block, what this means is that this conformal block, the nice way of writing it, is to write this conformal block fk 1, 2, 3, 4 that depends on x1 up to x4. The way we should write it is taking out this factor, x1 minus x2 to the power 2 delta, x3 minus x1 to the power 2 delta, times some conformal block, f, let's call it maybe straight f, k, 1, 2, 3, 4, that will only depend on cross ratios u and v. It's a very nice check that we didn't do any mistakes. So when we will start computing these tensors b and so on, and you will use conformal algebra, at the end of the day, typically you do some mistake in mathematics, and at the end of the day, this doesn't work. It's not just function of u and v. And then you debug until it is just function of u and v, then you are confident that you did no mistake. Okay? This happened to me a few days ago when I was preparing these lectures. Okay, very good. And generically, this f, this k index, what is this k index? We can represent this k by saying that we consider the delta of the operator and the spin of the operator. Even though in this stuff I did not discuss the spin, what would change if the operator OK would have spin? I would have to, the only thing that would change is that in this 3-point function, I would have to compute a 3-point function of an operator with spin with 2 scalars, but that I said it's fixed by conformal symmetry. And actually in the homework for the weekend, you will play a bit with operators with spin. And another thing that would change is that in this game, we would start also here from the result with spin, which would reshuffle a bit this algebra. Okay, but it's just a technical, it's just technically a bit more involved, but conceptually everything would go through. So then, what we get is that the final expression is that the 4-point function is given by some sum over k. Okay. Now for 4 operators which are the same, O would be given by 1 over x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta, sum over operators of dimension delta and spin L, C1 to k, C k 3, 4, where k is this operator, and then some known function that has labels delta and L, and it also knows about the external operators. It also knows about delta 1, delta 2, delta 3, and delta 4. That is a function of cross ratios u and v, or alternatively z and z bar. Okay? Remember that this is equivalent to u and v. I remind you that the definition was that u was just z bar, and v was 1 minus z, 1 minus z bar. Okay? I'm just writing z bar because explicit expressions are a bit nicer in terms of z bar rather than u and v. Okay? But what is extremely important to emphasize, what definitely is important to emphasize, is that the set of deltas and structure constant fixes the 4-point function. And higher, of course, we can just repeat. So this means that what you have to compute all correlation functions in a conformal field theory is a set of dimensions and 3-point functions. The rest is just purely kinematical, and it is just about gluing picture like this. If you have 5-point function, you have one more leg coming out in the middle, you just, in a sequence, apply the OPE. The OPE structure is totally fixed by symmetry. So in this way, you get any correlation function. Okay. Any question? Is it too slow? Yes.
So the way it was done there, it seems to me that since we only choose here this function of operators x1 and x2, like we have to like have like symmetry between what happens between x1 and x2 and x3 and x4. It seems to me that the radius of convergence will depend only on the distance between x1 and x2 and not between x3 and x4. Is that
I do not want to go much into the details of the radius of convergence, because it so turns out that after you resum everything, after you resum all these descendants, you now have a function of u and v. So if you manage to resum, if you manage to write analytic expression, so if you work with sums, if by this f you mean a sum, and you work with a sum, with truncated sum, your statement is right. Then the radius of convergence is the same that I drew above. It's related to some intersection of two circles. However, if you manage to compute this sum analytically, you increase your radius of convergence, and it turns out to be the full plane. Okay? It's very much the same as, imagine you have a function where you have, say, 1 over x squared plus 1. It has a radius of convergence, which is 1. But if you manage to resum it, okay, now it's a function, you can go everywhere in the complex plane. So it is actually similar here, but it's kind of a subtle point that if we manage to write analytic expressions for this guy, then our radius of convergence actually improves a lot, even more. It was not only finite, it becomes, if I'm not mistaken, the full plane, actually. Okay, so is it clear that a priori, if we were powerful enough, and actually my goal, one of the things I'm considering is whether I should show you how to fix this function explicitly, say by using Mathematica and just computing many coefficients, seeing some pattern and seeing what this is. Maybe it would be nice to do it on Monday. But is it clear for you that a priori I can compute all these coefficients, and therefore this square bracket is totally fixed? Is that conceptually clear? So then let me write to you what the result of this is. And to introduce the result, so explicitly, the result is the following. First of all, it's useful to introduce some function, h lambda of z, which is defined to be z to the lambda times some hypergeometric function. Okay. Do you know what hypergeometric function is? Just defined by some series with some Pochhammer. Pochhammers are some ratios of gamma functions. It's some simple function, okay? Have you seen? Did everyone see hypergeometric functions? Yes? I mean, you can just Google easily. It's defined by some series. It obeys some generalized differential equation. It's something simple. Okay, so this is some hypergeometric function. And then the conformal blocks can be written very explicitly. So that f that we wrote there of delta and L of z and z bar is equal to, now we have to specify in what dimension we are. So in 4D, for example, in 4D, it appears it is the following. It is z bar over z minus z bar, h of delta plus L over 2 of z, h of delta minus L over 2 of z bar, plus the same thing with z and z bar exchanged. So you see that z is a very nice variable, z and z bar, they are very nice variables. If we were to solve for u and v and write them as u, it would be a bit messy. And in 2 dimensions, for example, it would be 1 instead of this factor, and then here the same thing. And that's it. Okay, very good. And what else do I want to say? Okay. Okay. So now, again, let me just come back to this picture of the cylinder. You can again imagine that you have 2 operators here below this yellow line. You have 2 operators above the yellow line. The 2 operators above define some bra. This guy defines some cat. And the 4-point function should be just the overlap between those 2 states. And this is exactly what these kind of cartoons indicate. You just take 2 operators. You see what state they effectively generate. You take 2. You see what state they effectively generate. Each of them generates a sum of states. And then all you have to do is overlap them and the states will be orthogonal and so on, and this overlap will be just a sum of states, which is nothing but that sum over there. So it has a very natural interpretation, this expansion, in terms of this picture in the cylinder. Okay, very good. So let me just now mention a few words in the remaining 2 minutes about, let me just remind you that about what would we generally need to do if we want to generalize a bit this kind of construction. So one thing that I told you is that we could do general spin, and I even wrote the expression for general spin. You just have this L there, and things don't get much more complicated. But you could ask, what about external operators with spin? Not internal, but the external ones. What if I also consider external operators also with spin, like vectors or tensors and so on? Okay? So in that case, you can ask, did people work out these conformal blocks? Now, if you have tensors as external guys and try to repeat, things become so messy that it's basically hopeless. I mean, in principle, you should be able to compute. It still should be more or less very constrained by conformal symmetry, but it's basically hopeless. And actually, this approach, even though it is totally fine, and we will see on Monday how it does work explicitly, and we will derive, I hope, these results for 2 dimension on Monday. But even though this approach is perfectly fine, in practice, it's not the way we currently think. The way people now compute these conformal blocks is by separating these 4 points into a sphere that encapsulates 2 points and a sphere that doesn't, and acting with the Casimir of the conformal group on 2 of the points. It's like measuring the total angular momentum. The Casimir acting on 2 of these points, on the one hand, they act as some differential operator on these points. You just build the Casimir out of the generators. The generators, you know how to act on operators. So the Casimir acting on 2 points, it is just some differential operator. Is it clear? On the other hand, you can move the Casimir from the 2 operators to the Casimir acting on the operator OK that they produce. Because the Casimir acting on the full system should be 0 because it's just conformal invariant. So on the one hand, you get a differential operator acting on 2 points. On the other hand, acting on just a single operator that is being exchanged, it just measures its conformal Casimir, the analog of jj plus 1. And by comparing both, you obtain a differential equation for the contribution given by the exchange of an operator OK. So there is a technique of immediately deriving what kind of differential operator should this guy obey by saying that this guy describes an exchange of an operator with a definite Casimir under the conformal group. Exactly in the same way that you can find expressions for spherical harmonics by imposing that these are functions that are definite Casimir under the rotation group. It's not different from that. Actually, this technology was developed around 2004 by Dolan and Osborne, this technology of these differential equations. But even though it's much more powerful and it allows us to generalize this very easily, it is still not powerful enough to deal with tensors. And to deal with tensors, it was necessary to develop some technology based on this embedding formalism that you have seen on the tutorial. So people were playing with this 6-dimensional formalism, or D plus 2-dimensional formalism, where conformal symmetry acts just as Lorentz symmetry. It's a very powerful constraint. And the first problem that was solved in 2011 was to understand how to consider all possible 3-point functions that you could have between arbitrary tensors. So just 3-point functions. Label all possible 3-point functions. What are all possible tensor structures you can have and so on? How many are there? How many structures you can have and so on. Remember that the C1 to K, they have in general an index Q if you are dealing with tensors. So fixing all these structures. And only last year, Simon Duffins understood how to use these general 3-point functions with spin together with some nice differential operators to obtain the conformal blocks with spin. So this is, if you want, a very new result about the study of these functions. So the way I presented also these conformal blocks last year, and the end point was very different. I have the notes here from last year, and at last year I ended saying the conformal blocks are not known with spins, the 3-point functions are barely known. And the situation improved a lot in the last year concerning what we know about higher dimensional CFTs, including operators with spin. Another thing that you could say is that somehow I wrote here 4 dimensions, and I wrote here 2 dimensions, and no one knows what's the result in 3 dimensions, which is kind of funny. So in 3 dimensions, there's no closed expression for conformal blocks. You can write a series expansion, you can have some kind of recursion relations, but no closed form for conformal blocks is known in 3 dimensions. So maybe next year, this will be different, hopefully. Okay, so I have 2 options now. One option is to say, okay, this is the end of the crash course on conformal field theory. So we have seen that the conformal field theory is what the conformal field theory is, how it arises as endpoints of the renormalization group flow. And we have seen that contrary to quantum field theory, conformal field theory is, the extra symmetry that we gain out of conformal field theory is indeed extremely powerful. So to solve these quantum field theories, conformal field theories, we only need a set of numbers, which are the dimensions and the structure constants of the operators. It's a huge simplification, right, over usual quantum field theory. And this, let me end maybe with a definition. Okay, I will go a bit over time. With a definition of a conformal field theory, a modern, if you want, or an alternative definition of a conformal field theory. Actually, no, I will not. So now, well, let me just conclude my words. So the option now is either stop here with conformal field theory and go to AdS CFT, or still cover a bit of some more advanced topics and finish some loose ends about what we have covered so far on Monday and Tuesday, and then go to AdS CFT on Wednesday. And I'm willing to receive feedback from you, and please tell me what you think would be you would prefer the most, and are you eager to know about AdS CFT, or would you rather like to know some more details about, say, how to compute these functions in practice? How can we use this kind of cartoons to constrain even more what the behavior of conformal field theories could be, and so on? Okay, that's it. So let's continue next week.